been talking a lot already. We're not even doing our lesson yet today. What are you guys saying? Yeah, I know. All right, so today 6.1. So this is the lesson eve of Math Excel assignments, of actual textbook lessons for this term. All right, so differential equations and slope fields. So this is probably the easiest thing that we're going to talk about this slide all year potentially. An equation involving a derivative is called a differential equation. Okay, nothing mind-blowing there. So don't be intimidated or thrown off guard when you hear the term differential equation. That just means that's the derivative function, the derivative equation. So if I gave you an equation, ask you to find the derivative of it, that new function that you have or that new equation is called a differential equation. So the thing is, we're going to be working with the derivative, but we're going to also be able to backtrack. If given the derivative, I can tell you what the original function would be. All right, so let's do this. This is almost like a warm-up as well. Find all functions that satisfy dy dx. So again, this is a differential equation. This is a derivative equation. So if the derivative equals secant squared of x plus 2x plus 5, what is the original function, or more specifically, what are all of the original functions that will satisfy this? Okay, so we're trying to find our function y. So we're going to anti-differentiate or find the antiderivative of each piece. So what's the antiderivative of secant squared of x? Tangent of x. The antiderivative of 2x. Okay. And then the antiderivative of 5 would be 5x. But now all of them, we need to tack on that plus c, because it says find all functions that have this derivative in red, the dy dx piece. So all functions would be tangent of x plus x squared plus 5x plus c. Because of this plus c, this is what's called a general solution. So in general, they don't give me any more information. They just say find all functions. I'm going to have this plus c attached with it. But now, if they expand on this, if they give us additional information, such as the value of a function at a single point. So say they say, well, that dy dx, they give us the derivative function, but then they say, well, f of negative 18 is equal to 3 or something like that. So they might give us more information also. If they give us more information, we can determine the particular solution to the differential equation. So if a general solution, they'll have that plus c, but if they give additional information, I can be more specific, and that particular solution will not have that plus c. We'll actually be able to figure out what that c is based on them telling us that f of negative 18 is 3. Okay, all right, so new problem. They give us a differential. They say dy dx is e to the x minus 6x squared. And they say, okay, well, what is the general solution? So again, paying attention to these variables. So this is saying dy dx, the derivative of our function y with respect to x. So we know it's going to start out as y equals. So don't glaze over that information. Don't just look at it, oh, dy dx, it's that fraction, it's Leibniz notation, it means derivative. Don't glaze over that, because if they said dt dx, and then you start out and said, well, y equals, and kept going, that would be incorrect. Okay, so my function, the derivative of y with respect to x, means I'm going to have some function y, and so this is e to the x, and then what? Minus 2x cubed plus c. All right, that's the general solution to it. So if I take the derivative of that, no matter what my c is, I will end up with the derivative e to the x minus 6x squared. But now, the same differential, but they give the stipulation that our function y that we find has to pass through the point 1, 0. All right, so we're going to try to find the exact function that satisfies. If I put 1 into it, I get an output of 0. But also, if I take the derivative of it, I end up with ex minus 6x squared, or e to the x. Okay, so we know our general solution was this e to the x minus 2x cubed plus c. Now let's use this additional information. Well, I know x is 1 and y is 0 from that coordinate. So then I could say 0 equals e to the first minus 2 times 1 cubed plus c. And so this is e minus 2 plus c. If I wanted to solve for c, I could bring this e over to the other side. Plus 2 equals c. But now my particular solution, I'm going to jump from this step right here, and I'm going to say now my particular solution is y equals e to the x minus 2x cubed minus e plus 2. That function right there will satisfy having a derivative of e to the x minus 6x squared. And if I put 1 in, I will get an output of 0. Okay, let's look at it another way. So find a solution to the differential equation. So this says f prime of x is e to the negative x squared. So instead of you writing it in that Leibniz notation, they're just saying the derivative of f with respect to x, that's the same thing, f prime of x, equals e to the x squared. But then it gives this initial condition that f of 7 equals 3. So they only said find the solution without writing it out explicitly. We need to find the particular solution. We're not going to have any plus c. If they give us an initial condition, we're not going to have a plus c to go along with it. Okay? Well, if f prime of x is e to the negative x squared, if I wanted to find f of x, I would have to integrate. And so f of x would be my integral or my antiderivative of this function, e to the negative t squared dt plus c. And I'm going to be more specific here. I'm going to put some bounds of, we'll just say a to x. Okay, because I know if I were to take the derivative of my integral, if I were to differentiate this, I would end up with f prime. So let's just actually do it. Let's make sure we're comfortable with this. So f prime of x would be d dx of this integral from a to x, e to the negative t squared, dt plus c. Okay, I'm taking the derivative of all of this. So my c goes away. That part 1 of that fundamental theorem of calculus then tells me I'm going to have e to the negative x squared. Okay. All right, now I'm going to erase this actually a minute because I know my next thing is going to pop up right over top of it. So I'll give you a second to write this down. So what I have there in purple is valid. If f prime of x is e to the negative x squared, then I could say, well, f of x is going to be the antiderivative or the integral of all of that. And now using this initial condition, I would say, well, f of 7 is going to be equal to my integral from 7 to x. Well, let's just leave it as f of x. F of x is going to be equal to my integral of 7 to x of e to the negative t squared dt plus c. So now f of 7 would be from 7 to 7 e to the negative t squared dt plus c. But I know f of 7 is really 3. My integral becomes 0 plus c. So c in this case is actually 3. So my integral, I want to be very specific here, it's only 3 when I'm going from 7 to x e to the negative t squared dt plus 3. That is f of x. So this one's a little bit, this one requires a little more thought, understanding what's going on with integrals. We know integrals are the antiderivative, but then when I put in the bounds there, understanding, okay, f of 7 equals 3, how I can use that information to determine what my c is, and then come up with my final function. So we're not used to seeing a function, or I mean, we have seen it, but not enough to recognize that this is a function. If you told me to put in 7 to that, I would get 3 as an output. If you told me to put in 10 to that, I would get a number as an output. All right, so that's with differential equations. Now we're going to talk about slope fields. Okay, so on this first slide, I say graph the general solution to the differential equation dy dx equals cosine of x. So the general solution, I know it's going to be in the form of y equals, and it's going to be y equals what? Sine of x plus c. Now that c just represents some constant. So c could be -5, it could be 100. Okay, so c can change. The sine of x is not going to change. So if I were to graph just the general solution to y equals sine of x plus c, the only thing that's going to change is that shift that may be going on. So this green line here, this is y equals sine of x plus 0, because if I put in 0, sine of 0 is 0. If I wanted to do sine at pi over 2, I would be here at 1. Here. So again, sine is the y value. Right here where it's crossing at, that's going to be sine of pi. So if I go around the unit circle, I'm at pi. Sine of pi is 0. 3 pi over 2 would be at a -1. And then out here where it's crossing again, that would be at 2 pi. So that green line is the sine function. But now if I change it up to say this purple line, so So this purple line here is y equals sine of x plus 1. The line above that would be sine of x plus 2. Or I could go down, and I could say, okay, this would be sine of x minus 1, sine of x minus 2. So graphing this general sine of x plus c, I'm going to have all these multiple waves, okay, that are mirror images of each other, but they're just shifted up or down. So that would be the graph of a general solution. But we are actually going to use differentials and graph a differential rather than graphing the solution to it. Okay, so this would be the first time we've graphed a derivative function in terms of a differential. And how we're going to do that is what's called slope fields. So slope, and that's the same dy dx, that's slope. So if they tell me dy dx equals cosine of x, that tells me I can find the slope based on cosine of whatever number I put in or whatever angle I put in. So slope fields allow us to produce the graph without actually solving the differential equation. So if they tell me the differential, I can graph the y equals function. So if they tell me that the slope is represented by cosine of x, I can use that information and graph the original y equals function. How I do that, again, that differential equation gives us the slope at any point, and we can use that information to draw small segments. Sorry, I don't know why my voice cracked there. Small segments at specific points. Okay, so let's actually do this. Let's construct a slope field for the differential equation dy dx equals cosine of x. So first off, let's look. Well, we know cosine of 0 is equal to what? What's cosine of 0? 1. Okay, let's actually, I'm going to do it in green. So cosine at 0 is 1. That means the slope of our line at 0 will have a slope of 1. And so I would draw just a little line segment that has a slope of 1. Just a small, like almost little like hash mark. All right. I know that cosine at pi over 2 is 0. And so at pi over 2, I'm going to draw a horizontal line which has a slope of 0. And I moved up because I know when it's 0, my y value is 1. So that's why I drew a horizontal line at pi over 2, comma 1. Okay, cosine at pi I know is negative 1. And so my coordinate would be with a negative slope or negative little line segment going right through the x-axis. And then cosine at 3 pi over 2 would be 0 again. And so that would be a little line segment with a slope of 0. So again, these little line segments represent the slope. So if I were to start to connect these, if I were connecting these, I can see my curve starting to take shape. And I could go negative as well. This would be 0. This would be a negative 1. This would be 0. This would be a positive 1. And so we used the derivative and the idea of slope fields to construct the graph. This graph is y equals sine of x. And we've already seen this, but this graph can be shifted up and down. And so here on my y-axis, they will always have a slope of 1. At pi over 2, they will always have a slope of 0. At pi, they'll have a slope of negative 1. No matter what constant c I have going on, it's always going to have a slope of negative 1. And then again, 0, positive 1. So this is what a slope field will look like. Will look like just a bunch of these little individual line segments. Okay, and so I'm going to keep filling this out so we can see exactly what's going on. So this is what they will give you with a slope field. They'll just give you a graph with all these short little line segments, but we need to recognize, okay, each line segment, that simply represents slope. And we can see, well, if we start to connect these, like if I chose this one right here, I'm getting my curve going on. So if I connect these line segments, it will create the curve of the original function y. But I graphed the original function y using slope. So you'll be presented with problems that'll ask you to interpret a slope field and determine what that original equation would be. Okay, once you start doing these aren't too difficult. Once you start doing them, they'll start to make more sense. Right now, it just probably looks like a bunch of dashes on a piece of paper or on the board. Okay, so 6.1 in Math Excel, due tomorrow by midnight. Tomorrow will be a work day in class. I think it's like 7 or 11 questions. Maybe it's 11 questions. Okay, should have plenty of time to be able to work through those. Get a jump on it tonight, and then finish it up tomorrow, ideally during class. Then you don't have to worry about having any homework for tomorrow night. And then Friday, we'll start the last lesson.